So you have done a lot of gravitation question, hopefully, okay? Or you've watched a few examples and you see that we look at gravitational force between normally planet-sized object lah, okay? We got 2 planet lah, 2 star lah, 1 star, 1 moon lah, moon lah, planet, satellite, okay, got a lot of stuff, okay? But in this question, which is very recent and very, very anomalous, which I love so much, this question, it is actually the gravitational force between 2 objects that we can actually see in real life. That's Newton's law still work. Okay, let's begin. So this question is from May 19 paper 42. It starts off light and easy. So we read the question. 2 point masses are separated by a distance x in vacuum. Okay, state an expression of the force F between the 2 masses m and m. Okay, name any other symbols used. This is 1 mark. Okay, so this is like a do or die question. You either do it perfectly and get 1 mark, or you make a mistake and then you lose a mark, and that would be sad. Okay, so here you want to find an expression for F. Hopefully you will know that this is G mm, but the separation is x, you know, so it has to be G mm over x squared. This one is not R, because they already say the distance is x. Okay, so we have x, we have m, we have m. The only thing that's left to be defined is your gravitational constant g. So you can say where g is the gravitational constant. Okay, that 1 mark. Gravitational constant is the same throughout the known universe. You go to new star, like Alpha Centauri or Tau Ceti, it's still the same. 6.67 times 10 to the power negative 11. All right. Anyway, here what we have is, you know, I say this one we can replicate in the lab. So there's a small sphere S here, this little tiny little ball here, okay? And it's attracted to one end of the rod as shown. Okay, the rod hangs from a vertical thread and is horizontal, okay, probably counterbalanced by the center of mass of the rod. The distance L from the center of the sphere of the thread is 8 cm. A large sphere L, okay, so small sphere is here. This is the top view, view from above. We see this from the top. Okay, so you can see this small sphere S, and you have this large sphere L. L for large. Okay, and it says that we place it close at 6 cm. Okay, and strangely, the initial position of the rod is here on this line. And it's like it gets attracted such that it tilts ever so slightly and gets attracted to L. So L is like, hey, small sphere S, I see you. I see you. Gravitational force. And of course, the gravitational force goes both ways because Newton's third law will always apply. But we are not measuring the reaction force on L. We are only measuring the force on S. How do I know? Because all the measurements are on S. Okay. All right, now let's just read the question. So basically, we start off in this initial gray position. Okay, it's just chilling. And then I bring the large sphere L close to the small sphere L. At 6 cm, this one begin to rotate towards. Okay, so put this one here. This one will attract S. Beautiful. Let's carry on. Ding, ding, ding. Okay, there is a force of attraction, you don't say, between the spheres S and L, causing the sphere S to move through a distance of 1.2 mm. The line joining the center of S and L is normal to the rod. Okay, show that theta that the rod rotates is this amount of radian. Okay, so this one we will use circular measure. Okay, so I've cropped it, okay, and you're asked to find theta. So we know this S, right? Okay, so I will use S is equal to R theta. Okay, and I zoom in a bit so you can see. This S is 1.2 mm. So we'll put 1.2 here. And then the radius is 8 cm. And then this is theta. Now, if your brain got alarm system, very good. You are sensitive. All these have to have the same unit. If one is cm, one is mm, tada boleh. Cannot. Okay, logic. So right now, you're going to change somebody. Okay, I'm going to change 1.2 mm to 0.12 cm. Okay, because 1 cm is 10 mm. And then this one I will keep as 8 because I like the number 8. Right, and now I can find theta. And also you will know your answer is wrong when you press your calculator and you cannot get it long. Divide by 8. Ta-da! So 0.015 radian, or you move the decimal point in 2 places and you will get 1.5 times 10 to the power of -2 radian. This is once again a do or die question. It's 1 mark. So to get the mark, I need to see this substitution here. This part is your A1. Actually, it's B1. Okay. Part 2. The torque of the rod, the rotation of the rod, sorry, causes the thread to twist. Okay. The torque T in Newton meter required to twist the thread to an angle beta in radian is given by this equation. So they give you equation. You may wonder, this 9.3 times 10 to the power -10 is what? Nah, it depends on the physical property of the thread here. You know, there's a thread that we hang it from, that it will cause it to rotate. It also obviously depends on the mass of the rod and where the center of mass is. So all that calculation is already done for us. We can just use the expression. Very good. Thank you, scientist. Or Cambridge question. So 9.3 times 10 to the power of -10 beta. Okay. So we want the torque through the angle that we just calculated just now, because the question says calculate the torque in the thread when L is positioned as shown in the figure. So as shown in the figure, we already calculated the angle, 1.5 times 10 to the power of -2. Okay, so we can just put these two together. Ding. So notice that I never cancel my answers, and when I don't do so, you know, the whole question becomes very smooth. I'm going to key in this one again. Okay, 1.395 times 10 to the power -11. If you want to follow convention of changing this to 2SF, you can 2 to 3SF, you can change to 1.40 times 10 to the power of -11, or 1.4 also can. All right, so pretty straightforward. This one again is a do or die question. It's only 1 mark. So to get the mark, I need to see this. This part is this one leading to this answer. So I need to at least see this line. Okay. All right. Next, so basically we found how much torque is needed to rotate the sphere S by 1.2 mm. 1.2 mm is very small. Okay, it's only about 1.2 mm. Yeah, it's very small. This angle is tiny, guys. You go and look at your ruler. What is 1.2 mm? It's very small. So they probably use some high-tech, high-sensitivity length measurement, not measured by eye, and put your meter rule down there. Okay, anyway, the distance between the center of the spheres S and L is 6 cm. Yes. So L is placed 6 centimeters away from S. Okay, let me copy this to bring this down so you can see. So L is 6 cm away from S. Okay. The mass of sphere S is 7.5 gram. So S is light so that it rotates easily. But the problem with it having a small mass is, although it rotates easily, it also means that it does not have a large gravitational force. Okay, so it's like a not so ideal situation. But the mass of S is given, the mass of L is given. By equating the equation in B2, okay, to the moment about the thread produced by the gravitational attraction, calculate a value for gravitational constant. Interesting. Okay, so if I look at this drawing, I'm going to just make it a bit bigger for us. Okay, if I look at this drawing, obviously there's some torque happening here, right? Okay, so we know the torque needed in B part 2, we already calculated, is this value. Okay, but we know that this torque is caused by Fg. So another equation that I can write about the torque is that it's equal to gravitational force times perpendicular distance. This one from your AS chapter 5. And you're like, huh, Miss, AS stuff need to remember. Ah, yes, AS stuff still need to remember, okay? So torque will be gravitational force or force times perpendicular distance from the pivot. This is your D, which happens to be 8 cm. All right, so I'm gonna bring the D over because I know I'm going to find gravitational force. I have torque already. I can substitute later, not a problem. So gravitational force will be G, mm, and if you want to follow the theme of the question, it will be over x squared. What are we looking for? Today, we are looking for the VVIP, gravitational constant. We're looking for G. So I'm going to rearrange everything. Okay, and what I will have now is G is equal to x squared bring up. So I will have T x squared over D, mass of the big sphere, mass of the small sphere. Now I can substitute. I gotta make sure everybody is SI. Why? Because this unit that my head is blocking is all SI. Gravitational constant all must SI. All right, so we have torque. Let's copy from the top. 1.4 times 10 to the power negative 11. Okay, I answer this question every year and I'll keep answering again. So I'll tell you now. Miss, does it matter if I put 1.395 or I put 1.40? No, it doesn't. Put whatever you want. Okay, you can put 1.395, you can put 1.40. But Miss, if I put 1.40 here and I put 1.395 here, can? Can. If I put 1.40 here and 1.40 here, can? Can. I prefer to not worry my examiner so much. So I'm thinking about my examiner. Hey examiner, I want to give you less work. And also, I want to stick to the sensitivity of the experiment. So the sensitivity or the precision of the experiment so far reported to me has always been 2SF. See? 2SF, 2SF, 2SF. So if all the numbers are in 2SF, then the largest I can go for a calculated value should be 2 or 3SF. So I'm sticking to this one. Okay? If you put 1.395, you probably will not be penalized, but you will just create an extra half a second for the examiner go like, hey, 1.3. Then the examiner will have to lift the head a few to see, oh, 1.3, okay. Yeah lah, so give them less work. Your life is easier. Okay, what is X? X here is the separation. It's the separation between the two spheres. So this 6 cm is equal to X. So 6, please convert times 10 to the power negative 2 square. Divided by, okay, what is D? D is the separation. You notice that I always label distances clearly on the diagram because, again, I am the kind of student that I could see myself doing this, you know, putting 8 here and putting 6 here. So I don't want that to happen. Okay, so I make sure I label everything correctly. This is 8 times 10 to the power negative 2. The mass of the large sphere is 1.3 kg. Mass of the small sphere is 7.5 gram, but gram has to convert to kg. So there's a lot of conversion situation happening here. All right, so just make sure you convert everything, and then there's a square here. Okay, I'm somewhat satisfied. Let's press our friend Casio, the calculator. You press together with me lah. I press correct doesn't mean you press also correct. Doesn't mean I'm correct too. So this is to show the real-time one. Okay, and why do I put brackets? So that if I want to edit, it's easier. This is for safety. For me lah, for me. You don't want also, never mind. Negative 2 divided by 1.3 divided by... So now there's a prefix, I'll put a bracket. Because just in case I forgot to convert something, it's easier for me to know which bracket to input my data. Okay, the I square, paranoid now. Ding, 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 ding. Okay, I did square. So now my gravitational constant is 6.46 times 10 to the power negative 11. So it's not exactly the value that is given to you, or the known value, but I think it's close enough. So if you want to declare this in 2SF, because, you know, all the measured value is 2SF ma. So you can call this as 6.5 times 10 to the power of negative 11. Hashtag close enough. Okay, so this is the value of your G. Where are the 3 marks? 1 mark is when you equate torque to gravitational force times distance. This is your C1 mark. 1 more mark if you substitute everything correctly. Of course, you can find the gravitational force first. You can put in the 1.4 times 10 to the power negative 11 and divide by D, which is 8 cm, to find the gravitational force. That part will give you your C1. Okay? And then after that, you substitute all the other values. You will get another C1. And the final answer, correct, is A1. So it can be 6.46. It can be 6.5. Did I press wrongly? I don't think so. Negative 11. Sometimes, if let's say you find the gravitational force separately and you put in and you round, it's slightly different, it's okay. Don't worry about it. Your answer is not wrong. Just make sure you show your substitution very clearly. Show your substitution very clearly. Because if I look at the mark scheme, which I am right now, what they probably did was they calculated F. Okay, and probably some value here is lost in translation. But you can see that all the things that I substitute is correct. Okay, all the numbers are correct. Everything is the correct prefix. So the reason they got 6.4 is probably because they didn't press the whole thing in the calculator. They did some rounding. Okay, so as long as your final answer is close by 1 SF away, like 0.1 in this case, it's okay. All right, you double check your calculator lah. I think I pressed correctly. Negative 11, 6 times 10 power negative 2. Yeah, pretty sure it's okay. All right, so this is this part of the question. Now we are ready to move on to the last part. Okay, this is the second part that I didn't crop in. Okay, suggest why the total force between the sphere may not be equal to the force calculated using Newton's law of gravitation. So basically, when I calculate F using this equation, you really can tell that the gravitational constant is close enough, but kind of far also. So why is the answer not accurate? 1 mark. There are many reasons that you can say to why the answer is not accurate. Because when I measure this thing, right, if I am talking about sensitivity of something like 1.3 kg, your body is more than 1.3 kg, right? Wouldn't your body exert a force on it? Wouldn't you have other objects on it? So the first thing I can think about is there could be other objects around with mass because these masses are not isolated. So I can say L and S, which is the sphere's name, may not be isolated. So the force is affected by other masses between, whatever you take and measure. Even if you are not in the lab, you are in a lab, right? The lab has mass, the wall has mass, everything has mass. So it's kind of sus. Okay? So other things that you can say is, because you don't know the material, so you could say L and S may have static charges. So because of this, there is electric force. It's very hard for any of us to control electrons, okay? So how do you know that there are no electrons here? Don't know. Okay, so here are other acceptable answers. So these are the easiest one to think about lah. For this to apply, for your GMM over X squared to apply, the mass have to be isolated, meaning they're on their own. Means the planet one isolated, the planet one quite isolated, you know? You are alone in outer space. The Earth and the Moon be like just you and me, bro. So yeah. Other answers that are accepted includes The law only applies to point masses and the spheres are not point masses. Okay, sure, because the sphere may not be uniform. So I think these two carry the same meaning. Okay. The second problem is you could say, you know, the radius of the sphere is not small. Yeah, compared to the separation. Okay, I prefer this one. The masses are not isolated. And the fact that the masses are not isolated is the same as there could be forces between L and the rod. You think L and rod wouldn't interact, meh? So when we say not isolated, we can say they could be rod lah, maybe your measurement device. Even if you put a camera there to capture, the camera also have mass. If you are in the room, you have mass. Okay, so it's very hard to put an object on Earth in a massless place. Very weird. Okay, the spheres may be charged. Okay, there can be electric force. Why can't we talk about the gravitational field of the Earth? So I do not accept, cannot, the fact that the gravitational field of Earth not allowed acts on L and S. This is wrong. Why? Because the rod is horizontal. Okay, so the rod is horizontal, so you cannot say that, hey, actually, got other gravitational field, we are on Earth, right? Yeah, but it's okay. Look at the way we hang the rod. Let me show you. This rod is horizontal. Any form of weight, okay, will act in this way. Mg will be here, Mg will be here. Okay, so when you look from the top, Mg is not able to exert any torque at all, because we are looking at the horizontal oscillation, not the vertical tilting. It's as if like we are assuming that the gravity is 90 degrees to this. The gravity of Earth is 90 degrees to the gravity between L and S. Gravitational force of Earth is 90 degrees to gravitational force of L and S. So that is what we mean by, if you were thinking, what about the gravitational field on the Earth? Well, I commend you. Not many people would think about that. Okay, but we cannot because the rod is horizontal. So because of this, Fg of Earth is 90 degrees to Fg of L and S. So it won't affect each other, 90 degrees. All right, that's it for this strange question. Okay, so for an interesting deep dive into this particular question, okay, when it comes to gravitational force between two small objects, these are the limitations, and there are other limitations as well. Okay, so there's a really cool minute physics video that I will link down in the description. You can go and watch that one. I'll see you in the next video. Bye bye.